All right, so per the discussions we've been having so far, we've come to the understanding that it's very important that for every system you have a particular control system for it. So that will mean that there's a designing part, right? Yeah. So if you want to design a control system for a particular plant or particular facility, there are a whole lot of things that you must consider, because you can't just give any control system to one control system to all types of systems. It will not work, right? Yeah. So most of the times what happens is that we have to put the designs, the concepts together, understand the phenomenon that happen within the whole system itself before you're able to design the control system for a particular system, right? So generally there are some things that are considered. Yeah, these are the main things that are considered when you're designing a control system, right? So we have one. You basically have to select the objectives, right? Yeah. And most of the time these objectives, it could be quantitative or qualitative, right? So let's say for this one, for instance, the objective is that you want the output temperature, or the temperature that comes out of this tank, to be, let's say, if you say quantitative, so you specify the particular temperature. So let's say about 90 degrees Celsius, right? So that's quantitative. You're giving them a value to it, right? Or it could be that you describe it qualitatively. Oh, I want the output temperature to be about. So let's say the output temperature, which is T, you want it to be about. You want it to be. So let's see. So maybe you want the output temperature, which is T, to be equal to about 90% of the input temperature. So that's basically, you have kind of like described it 90% of 90%, right, of the input temperature. So somehow you've described it qualitatively, right? But then this also can be translated to qualitative. So you've described it qualitatively, but this can be described quantitatively, right, in terms of numbers, right? And then if you want to achieve a particular objective, right, that's now you describe temperature, right? So some of these, so the thing that your objective, can it be controlled directly? Can it be measured directly, right? If it can be measured directly, so after you selected your, what's the name, the objective, so now you select your measurement as well, right? Select your measurement. Some of the objectives you have to measure it directly, some of them you have to measure it indirectly, right? It depends on the system. It varies the system as well. And then after you select done this too, now you select your configuration, right? The configuration is basically the control system setup that you want to choose, whether feed forward, feedback, cascade, ratio, a whole lot, or even direct, what do you call it? There's a DCC, right? Which is basically kind of like electronic, right? There are a whole lot of control systems that you can choose from. So it could be direct digital control or any other one I want to do. So now you select your configuration, right? Configuration, right? So now that you've selected the configuration, so now you know the objectives, the more single or more. You selected the measurement, whether direct or indirect. You selected the configuration. The next thing will be for you to select the instrument that you want to use, right? Because now that you selected your configuration, you will know the instrument that you need in each part of the configuration that you selected, right? So that will be the instrument, right? And each one of these steps is very important when you are designing. So somehow let's name this 1, 2, right, 3, 4. So these are the steps when you are designing a control system for a particular plant, right? Yeah. And as we've said, some of the objectives you have to measure them, you have to measure them directly, right? Some of them you have to measure them indirectly. So like for temperature, for instance, you can measure it directly. For concentration, if it's in a huge system, you have to measure it indirectly, because to be changing on, you have to find ways to measure that, right? Yeah. And then for, you see, we have something we call, so let's see, within the system, when you design a system, you have the input, right? So let's see, you have the input, right? And then you have the output, right? Yeah. And then somehow you want to be measuring these things. So when it comes to the input, some of them you measure them directly, some of them you cannot measure them, so they sort of become what's the name, what we call disturbance, right? So some of them you control them, you are controlling them, so it's like you are manipulating them in order for you to get what you are looking for. And the ones that you cannot manipulated. Let's see, yeah. So the ones that you cannot manipulate, this will become what we call disturbances, right? Because you cannot control them, especially for the input. So disturbances, right? And for the output ones, there are some that you measure to see what's happening, especially if you are using the feedback for instance. There are some of the outputs you'll be able to measure them directly, right? You'll be able to measure them, measured. Let's make a measure to measure them, and then the other ones you'll be able to measure them. So it depends on, you have to consider all these even before you design the system, right? You don't get up and then just design the system. So non-measurables, right? And these are all considerations that we consider, right? Yeah. And then whenever we are doing all these things, right, as we said, control systems and some to some point now we've been seeing some equations, right? But then you cannot measure something that you cannot control something that you cannot describe mathematically, right? So now we've said a lot of words, so now we're going to go a bit into it, right? All these systems, even something like this continuously stirred tank reactor, right? There will be an equation that will help you to describe it, right? There will be an equation to help you describe it. But then in order for you to get this equation, there are a lot of approaches to do that, right? So when we are using math to actually describe a system, that's when we say we are modeling the system, right? Basically we are describing the system in terms of math. Before you even control the system, you should be able to describe it first before you can control it, right? So modeling of the system, right? So that's what we call modeling. We're basically using math to describe the system. And then there are different approaches, or there are different ways of going about this, right? So yeah, one approach is that you actually do the experiment, right? Experiment in the sense that you set up the system, you don't know what describes it, and then you measure, you control, and use the equation. You get the final equation to describe it in the end, right? So let's see. So that's why we say you are using the experimental approach, right? Experimental approach. But then there are at times too that another approach that you can use is the theoretical, right? Because for the experimental, if let's say we have a system like this, and then someone has put in the effort to use let's say experimental control to describe the whole system, right? And the system is working fine, but then something happens, right? And then we even have to change even just the thermocouple. Even just the thermocouple that has changed can change the whole equation that's describing the system. Right, so somehow it's not advisable to use this, right? Just slight change within the system, even if the size of the equipment or anything is changed slightly, the whole equation will have to change, right? Yeah, but that's one way of doing it, experimental approach. Another way of approaching it is that we do what we call the theoretical approach, right? And the theoretical approach, what it does is that basically you look at the phenomena behind the system, right? And then there will be a general equation describing the whole system, right? And after you do that, if there are some assumptions, you put them in the equation, help you to eliminate some things within the equation, then you get an equation that describes the system, right? And then all these approaches, even if some are not here, the approaches that help you to describe the system, they all end up with the end result that you get after modeling the system is what we call a differential equation, and generally it becomes what do you call it, ordinary differential equation, ODEs, right? So you end up with an equation that's an ODE that's describing the whole system, right? That describe the whole system. But then one issue with the ODEs is that most of the times you can't tell what is happening at a particular time, right? You can't generally tell what is happening at a particular time. But then for these ODEs, there are different ways of solving it, right? There are different ways. So let's see. For instance, you could have an equation like this. So let's see. So let's see the x. So this differential equation, right? And it is clear that it's a third order differential equation, right? So let's see. So we have something like this, and we have this, and we have this, right? And we have d squared x. Right. It could be every which way. Every system could have This one equation that describes it, right? Fine. But what if you want to know what is, so let's say that will mean that this quantity is, let's say if this quantity is temperature, right? I want to know the temperature at a particular time. It will be very difficult for you to find it, right? Because you are seeing a lot of differentiation. And here the case that we have is a third order, meaning that you have to do about at least three differentiations and find a whole lot of constant, right? For you to be able to understand what is happening to the what's the name? What is happening to the temperature or any quantity that's x. So it could be a conserved quantity or something, x at a particular time, right? But then there are a whole lot of ways of finding it, right? So we have what we call the Laplace domain, and then we'll talk about all these in a bit. We have the Laplace domain, we have the frequency domain, a whole lot of, but they all end up with the same solution, right? Laplace domain, we have the frequency domain, we have the Z domain, and we have something we call the Greek domain. It has something to do with what's the name? Matrices, right? Yeah. But what the Laplace domain is that, so before we come to that, we can see clearly that these ODEs are in what we call the time domain, right? So generally, when we describe these equations using the theories, right, they'll end up with an equation that is in the time domain, right? But then, as we said, we can't tell clearly what's happening to a quantity x at a particular time, right? So what each of them does is that they describe the quantity in a particular domain, right? So what this Laplace does is that it transforms the whole equation into an algebraic form, right? So here we have it in ODE, but then the Laplace changed the whole equation into an algebraic form, right? So with that one, you can clearly see what happens to the conserved quantity or the quantity of discussion at a particular point in time, right? But then let's see. So this equation here for this OD here, for instance, if you are using Laplace, it changes it, and then we'll look at an example. It changes to something of this form, right? So we end up getting something like this. We have x of s, right? So here, so the OD here will actually be x of t, right? Time domain. But here we are doing Laplace domain, so like kind of like s of x. So whenever you see this in the discussions, that's what it will mean, right? So transform all that function to something like this, right? So let's see, and then we have s cube plus 4s squared plus 5s plus 2. It transforms it to something like this. And after you've done, so this whole process here is what we call the Laplace transform, right? So the Laplace transform changes it to something like this. And then after this, we do what we call, so this Laplace transform is something of the sort. So we transform the function, right? I'm writing the symbol of how it's done. So it is performed on the time domain function, right? To this. So after we've done this, and they change it back to something that we call using what do you call it? Laplace inverse, right? Laplace inverse. So it's represented this way. Let's see. But then this one performs on the x of s, right? And then it gives you a simpler function in the time domain that is clear for you to determine what is happening to the what's the name? The function at a particular point in time, right? So let's see. Trying to get an example. So for instance, a process that is described by this ODE, right, has this ODE form, which is basically nonlinear. Using the Laplace transform method, it transforms this whole equation into a Laplace domain like something like this, right? That's the first thing that. So basically, this is what we call the Laplace domain, the Laplace transformation, right? So, which is denoted this way, and it's performed on the f of t, right? And we have this one, and it gives us this one here, right? And then this whole thing again is taken to what we call the Laplace inverse transformation, right? Which is to give us this one right here. Right? So clearly you see that this whole equation here, which is nonlinear, is transformed into something like this, which is algebraic. So like let's say at a particular time, let's say when t is 2, right? We could clearly see that we can easily point t is equal to 2 into this equation and get the quantity here, which is x here. A conserved quantity could be anything at all, right? So you actually see what's happening at this quantity x at a particular point in time. But when it comes to this one here, it will be very difficult for you to directly put in the time and then see what's happening to that particular quantity. So that's actually the essence of the Laplace transformation, right? That is one way of understanding the whole equation, right? As we said, there's Laplace, there's time domain, what's the name? There's the z domain, and the other ones that we talked about, right? All right.